usually I would derive the formulas 1 to 3 and other stuff, but it was said in the section that that would come in the problem, so I haven't done that as yet. The other point is the characters. I'd like to make a lot of examples, learning how the characters, and first the additive characters, what they actually look like. So let's take an example, F9. Which characters do we have there? We need then to know the additive structure. So the type of F9 with the additive structure. And I think it's type 3.3. There are 9 elements, and these form a subgroup, and the quotient has 3 elements, 0, t, and 2t, minus t. So the type is 3, meaning we can have 0 must of course map to unity, and then this could map to, say, the square root of -1 in the second quadrant, or its conjugate, and then -1 plus 1 gives 0, so the product of these guys must give unity, meaning it must be its complex conjugate. And of course the other choice, now we come for t. I think here we have 2 choices, either omega or omega conjugate. When we add these t and unity, we get t plus 1, so that's the product of these 2, omega squared. And when we add t and 1, the product gives unity. And now we do the same with plus 1. With minus 1. This one times this one gives unity. And this one times t gives omega. Minus t plus t gives 0. So the product must be unity. And then we can go along continuing this. Oh, let's just do it. Minus t plus 1, that's the product of those. Minus t plus 1, that's that. Then minus t minus 1 is minus t omega bar, minus 1 omega bar squared, and omega bar, that gives unity. So let's leave it for here. Now, the one they define in the book is trace, so we have 4 all together. We need to compute the trace, and the trace of 1, it's second order of F3. So the trace, it's a map from F9 to F3. So we need to know, or here it's just twice the guys. So trace 0 is 0, trace 1 is 2, or minus 1, and trace minus 1 is minus 2. The trace of t, that depends upon the the minimal polynomial we use, so we'll just use Mabel for that. I've here defined the Galois field of 9 elements, and in order to make the computations of various polynomials, I define 1 and 2 members of the field of 3 elements, and then we can compute the value of the 3 prime polynomials over F3. And you see there must be 3 polynomials. We have 9 elements here. 3 of them lie in F3 themselves, so we are left with 6. Each second order polynomial have 2 solutions, so that means that we have 3 polynomials. And now I was in a strange situation, knowing the number of prime polynomials over a prime field, but not being able to prove that they existed. And I looked into it a little, and finally I got an idea that it might be, I'm just digressing here, but let's keep, bear with me. Now, if we have prime polynomials of degree 2, over F3. So the point, I thought it was a total question of counting. So we have the number of polynomials and that's monomials of degree 2. So that's 3 times 3, there are 9. And then let's look at how many we can make that are not prime. They must be a product of 2 polynomials of degree 1. And of course we have 3 of those. Let's just do it in general with a p instead of a number 3. So this is p squared. And here we have p polynomials. As products go, we have p where it's 1 squared. And then we have where we take 2 distinct polynomials and multiply. And we have p squared polynomials altogether. That means the number of prime polynomials and that's 1/2 p squared minus half p squared. So that's p minus 1 over 2. And on the other hand, we have p squared elements. Of these, p already lie in the base field. And since it's an extension of order 2, every polynomial will have 2 roots in there, meaning that this is the number of prime polynomials. Oops, you don't do that. So you see the combinatorics fit. It's probably not elementary, but relatively simple combinatorial principle that gives us the existence of prime monomials. Now that's the same prime polynomials. But it was very strange to be in this situation where I knew the number of prime polynomials but couldn't prove the existence of even one. Now, the trace, back to the trace of t, that's here. So that wasn't the right polynomial. I just let Mabel choose the polynomial here. Neither was this. This is the minimal polynomial of t. And the trace is unity. So, and then minus t plus 1 as well. Minus t plus 1 has unity, and t has unity. All right. Then we take t plus 1. That was the first, which was just x squared plus 1. T plus 1, yes. And minus, oh, of course. That has vanishing trace. And then the other one must have trace minus 1, doesn't it? This is t plus 2 and t plus 1. It has trace 2. So that was the guy, and it looks very much like the one we would get if we chose omega up here instead of omega bar. So this is the guy that is used in this section out of the 4 possible ones. All right. And of course the number comes exactly from the type. It's 3 squared, so we have 2 degrees of freedom. And then it's totally defined by those 2 choices. Right, that's all I have to say about the additive characters. Next we come to the I'll just call them characters. And let's look at the finite field of 16 elements. That looks very much like an A. Oops. It's the multiplicative group. It has 15 elements. And that's 3 times 5. I chose this one because it has nice prime factorization. When defining a character, I'd like to take a generator and then see where it can map. And there are 15 elements, so we are mapping into unit circle with 15 points on it. So that's the range of the map. We need to choose a generator of this group. So how many generators do we have? There is one, and all the powers that are themselves generators, that's those powers that are co-prime with 15. And that's given by the Euler-Totient function of 15. So there should be 8. So let's have a generator here, and the unit element oh, this is unity once again. Now, g to the second will be a generator. G to the third will have order 5 generator. This will have order 3. This will have order 5. Generator, order 5, order 3, generator, order 5, generator and generator. They must of course be 1, 2, 3, 4, 5, 6, 7, 8 generators. We can take any generator like this one, and it has 15 possible images. It can be mapped to 15 possible ones, and if k is mutually prime with 15, then it's mapped into a generator of the cyclic map. I don't know where I'm going with that. If it's mapped into one of these, then it will have exact order 15, otherwise it will have a lower order. And of course the one where it's mapped to unity has order 1. The point of all this is that we have 15 different characters. Now, of order exact. Exact order it's called. And then all the powers will have and we have q minus 1 characters. So there are only so many, and they will all be generated by a generator mapping to this one. So take a generator and map it to the generator of the cyclic group, and then we have the powers, the identity, up to q minus 2. So that's the family of the generators, the multiplicative characters, I mean. All right. The next thing was the method. That was really wonderful. So I wanted to learn how to do it myself. Reading the last section, I worked a little on these circles. So I wanted to find the number of points in FQ. And now we assume good reduction, or rather, I think it's sufficient that P fails to divide N, so that this is non-zero. The number of solutions to this equation, and that's affine solutions, we disregard the points at infinity. So we sum first we take out the points where one of them, the cases where one of them vanishes. That'll be relevant in a second. So first, where x is naught, then it's not a sum, then it's just the number of solutions to y squared equals n. And then when y vanishes, it's the same. So it's twice the number of solutions to this guy, plus, and then we sum over x squared being equal to a, not 0. Times the number of solutions to y squared being equal to n minus a. N not vanishing, this is equal to the number of characters, or the sum of the values chi of n plus, and the sum over all a, where it's all characters of order 2, so we'll call them chi1 and chi2, where they must have order 2, so we don't want to write that here. And then we should formulate it so it becomes the sum j of chi1, chi2. Well, let's leave that for a moment. First, we need to have changed. No, we don't need to have changed order here. That's low. We need to take n out. Then we get 1 minus a divided by n, and we need to take it out here as well. Now we are reduced to sum over characters of order 2. And there are only 2, and they map to plus minus 1. Because they have order 2, and there are 2. That is when prime is odd, so we have to disregard 2 as well. And now I split up, taking the 2 characters. So it's the trivial character and the other. So we call them psi t and then just psi, chi, sorry. Now, the trivial one, that gives just 1, so that equals 2. And the non-trivial one, we don't know. Plus. The 2 trivial ones, then that gives unity times, and j of the 2 trivial ones was q minus 2. 1 trivial, non-trivial. And then j of the trivial with the non-trivial, I guess that was minus 1. Yes, it was. And here we actually have 2. They come twice. It's a symmetric guy. And then we have the 2 non-trivial guys. That's chi squared of n, which of course gives unity. And j of x, chi point chi. Now chi equals the conjugate, so here we can use formula 1, but it's minus chi of minus 1. Let's reduce 2. This gives minus chi of n twice, so they cancel. Plus q minus 2 chi n squared is unity. It's minus chi of minus 1. I actually thought the right result was chi minus 1 minus chi minus 1. I'm not sure about that though. I'm not quite sure about the result. I'll just make a break and check that. Well, guys, I just corrected an error in my procedure, and I will just make it a little bigger for you. So now you can check it out at your leisure. And then computed the number of points of 3, which are interesting. I did compute those as well, but I won't waste your time doing that. But here with 5, it's minus 1, and with 7 it's minus 1 to the power to r. I should have written r, but never mind. So that means that the formula I got here actually is the right one. And of course, when the prime p is equal to 4, to unity modulo 4, then this is always unity. And in the other case, it's minus 1 to rth. So this was the correct formula. And I'm sorry to say that that wasn't the one I got when I did it by myself earlier. So it's nice that I can get the right one. Okay. That was the preparation or the work I did while studying the section